We'll be talking about the generalized Schur partition functions and RG flows, and this is work done with Anirudh Deb, who is a student in Stony Brook. And this project started when I visited Stony Brook several months ago, and we discussed a very simple puzzle, which is well known in the community for the last 10 years. It's a small puzzle, it seems unimportant, but then discussing with Anirudh Deb, we transformed this puzzle into a bigger one. And this is what I'm going to tell you. So it will be a very small, well-defined result in the end, but I will try to touch upon different subjects in the field of supersymmetric quantum field theories that were well studied in the recent years. So I will tell you some very well-known stuff and some new stuff, and the boring stuff is due to me, and all the interesting stuff is, of course, due to Anirudh. Okay, so let me start with the general motivation or general setup. So one of the basic questions that we have in physics in general and in quantum field theory in particular is trying to understand strongly coupled systems, so going beyond the strong coupling barrier. So typically we start with some definition of a field theory using free fields or say lattice, something that we understand very well. And then we would wish to a regime of parameters where the system becomes strongly coupled and we lose analytical control over the system. So for example, we trigger a renormalization group flow and flow to the IR, and to go to the IR, we need to go through strong coupling regime, and we don't really know what happens in the infrared. Another thing that can happen is that we have a tunable parameter in this theory, and in some regime of this parameter, the theory is perturbative. We can compute everything, but then we want to go again to strong coupling regime and to understand the system there. So to do that, we need to have some types of, some kind of tools. And the tool that I will discuss today, or particular example of a tool, is an extremely simple one. So the tool works like that. You compute it in the regime of parameters where you can basically compute anything. But then this computation or this tool that you are using is independent of the parameter which you want to, with which you want to go to strong coupling regime. So this sounds a little bit trivial. So how something which you compute, say at weak coupling, can tell you something about strong coupling. But there are such computations, and we will discuss them. And so the point is that this computation here needs to be simple, but not trivial. It needs to tell you something about the strong coupling regime. And of course, there are many such tools that we know and love. The ones which work for many quantum field theories are anomalies and associated symmetries. And in recent years, this was generalized to beyond the standard, what is now called zero form symmetries, to higher form symmetries and to categorical structures. And there is a lot of work done about this. So these are some topological quantities, again, that you can compute here. And since they are topological in nature, they can penetrate this strong coupling barrier. If you are dealing with supersymmetric quantum field theories, you have additional tools. And this usually takes the form of partition functions. Some supersymmetric partition functions, which you again can compute here, but they tell you also something about strong coupling regime of the theory, and they allow you to penetrate the strong coupling barrier. Typically, these partition functions are related to some counting problems. So if this partition function has explicitly a circle, like you compute it on a manifold with a circle, so you manifestly are performing some counting problem. Not always you have a circle, but then if you don't have a circle, often you can relate the partition function that you are computing to some limit of some other counting problem. For example, you can add a circle, go to higher dimension, and then take the limit of that circle being small and relate the partition function to a counting problem. And because these are some supersymmetric problems, again, this is something you can take beyond the strong coupling barrier. Of course, dependence on parameters, on say couplings or RG scale is much harder, and this is what we ultimately want to understand, but we will deal with these simple tools which do not depend on parameters, but still tell us something non-trivial about fixed points. And by the way, if you have any questions at any time, please stop me and ask. So why do we want these topological quantities? So what type of information they can encode if they don't depend on parameters, if they don't depend on the couplings, what type of informations you can encode using such tools? And here are examples of physically non-trivial questions that you can ask and get some information about using such tools. So one physical phenomena for which these topological tools are useful is the phenomenon of duality. So for example, you can start from two different descriptions of a theory in the UV, say two different Lagrangians. They can even be in different numbers of dimensions. And then you deform these theories by some relevant deformations and flow to infrared. And you can ask whether these two different flows result in the same theory in the infrared. And these types of tools, like anomalies and supersymmetric partition functions, you can compute them in the UV. They can tell you something, and they are invariant under the renormalization group flow. So if the two theories flow to the same theory in the infrared, the partition functions have to be the same. Again, I stress that the starting dimensionality of the two theories doesn't have to be the same. For example, you can start from some Lagrangian in 4 dimensions, deform it by some relevant deformation, flow to a fixed point in 4 dimensions, or you can start, say, from a 6-dimensional CFT and geometrically deform it by placing it on some compact space, so that at low energy you get effectively a 4-dimensional quantum field theory, and you can ask whether this quantum field theory is the same. So there is, nowadays, there is a lot of geometric understanding of such dualities, such RG flows, possibly across dimensions. And this combination of geometry together with these topological quantities led to a lot of progress in understanding these types of dualities. Of course, if all this topological information that you compute here agrees, then you have evidence that the conjecture that the two theories flow to the same fixed point is correct, but it is not a proof. But if some of this topological information doesn't agree, this is a proof that the two theories don't flow to the same fixed point. Another thing that interesting question is the question of emergence. So you can ask, if you have some global symmetry in the UV, what is the global symmetry in the infrared, whether the symmetry is bigger or smaller. And this type of topological computations can actually tell you what is the symmetry in the infrared under certain assumptions. And this actually will play some role in what I'm going to tell you. And of course, you don't have to do flows. You can look at what is called conformal dualities, where you have two different looking Lagrangians, which describe the same conformal manifold. So there is some tunable parameter, which you can tune both in this theory and in that theory, and describe same theory, same strongly coupled theories, for example, using different Lagrangians. Okay, so we can test conjectures using these topological quantities, and we can come up with new conjectures in general. So this is the background, the setup in which I'm going to tell you a very small and concrete story, but this is the big picture in which these things are important. So I will start by discussing a certain tool, an example of a tool which is called a supersymmetric index, and I will emphasize some things about this index that we usually take for granted. So several slides will be a little bit trivial, but towards the end of the talk, I will say something non-trivial about this statement, or something at least surprising to me. So what is a supersymmetric index? So it is something that we can easily compute if we have a Lagrangian. Say we compute it in a UV. We count states or operators in the UV. We use state operator correspondence in a CFT to either think as counting, as what we are doing as counting states or operators. We count these operators or states with some weight. So we weigh these different objects with parameters, fugacities, which correspond to the symmetries which are preserved during renormalization group flow. And this gives us an information about the infrared fixed point. And these indices are invariants of the renormalization group flow. So let me emphasize how this works in practice. So say you want to compute the supersymmetric index in the UV. So you compute this some type of a supersymmetric thermal partition function in the UV, and it depends on various parameters. So this A1, A2, A3 are fugacities for various U1 symmetries that you have in your system. So you can think of this as these U1s as Cartan generators of your global symmetry group. Then, if you deform the theory with the relevant deformation, typically break some of the symmetry. So you say you add an operator to your Lagrangian, which breaks a U1 symmetry, a parameter for which is this A1. Then what you do in order to compute the index of the theory in the infrared, you simply set the parameter A1 corresponding to that symmetry to 1. Okay, it's a very simple computation. So you get a function which characterizes the theory in the infrared, but in fact it also, of course, characterizes the theory in the UV. The function that you get depends on less parameters, so you don't get the most general index that you can get for the theory in the UV, but you do get something which tells you both about the infrared and about the UV. And you can reiterate this procedure. You can turn on more and more relevant deformations and basically specialize this function that you started with farther and farther. You get less parameters, but this function, depending on less parameters, tells you something about all the theories in the RG flow. Maybe it gives you the full information that the supersymmetric index can give you about the fixed point in the infrared, but it also tells you something about the UV fixed point. Okay, so let me specialize even more and discuss the supersymmetric index, not in general number of dimensions, or not with general amount of supersymmetry, but something very, very, very specific. So what we will discuss are theories in 4 dimensions and which have at least 8 supercharges. So n equal to supersymmetric theories in 4 dimensions. We can write the index for these theories. Here is the general expression for the index. It always depends on 3 parameters, Q, P, and T. And these parameters coupled to symmetries that you have in n equal to theory. So you have SU2R times U1RR symmetry, and since you're quantizing the theory on S3, you have the isometry of this S3, which is SU2J1 times SU2J2. So you have the Cartan generators of this group that you can play with, and also you have the scaling dimension of various operators. And you're coupling these symmetries to some fugacities, so QP over T, P, and Q written here. And importantly, you turn on this e to the minus beta Q dagger term in the definition of the index. And notice that parameters that appear in the index are not most general fugacities that you couple to the symmetries. You only turn on fugacities for symmetries which commute with the choice of your supercharge. And then the index is actually independent of this beta. It's a type of a Witten index. And you have less parameters that you can turn on. So for general n equal 2 theories, you have this Q, P, and T. And you also can turn on parameters for global symmetries, which depend on the theory that you are studying. So always you have this Q, P, and T. And sometimes you have these AIs. We will usually set this AI to 1. We will not refine our index with global symmetry fugacities, but we will play with Q, P, and T. So in principle, this is an n equal 2 supersymmetric index, and if we have a U1R, it's something which maybe you can think that it is defined only for superconformal theories, but you can think of it also as some n equal 1 index, and as such, it can be defined for non-conformal theories. So that's how Rommelsberger originally defined this index. And this was made precise by Festuccia and Seiberg. So the idea is that if you have a flow, you are not computing the superconformal index. You are not using the superconformal symmetry, but there is some supersymmetry which is preserved along the flow. And only at a fixed point, the index, the supersymmetric index, becomes the superconformal index. So this is the general story of the index. And I'll give you an example how it is independent of renormalization group flows. So the simplest theory that you can consider is a theory of free fields. So let us take a free hypermultiplet. It is built from two half-hypers, two chiral fields, Q and Q tilde. And you can easily compute the index of this theory just by counting operators. So the index is given in terms of a special function, this elliptic gamma function, one elliptic gamma functions per field. This was done by the understanding that the index is related to special functions was observed by Dolan and Osborne in a very important paper, and I think it led this understanding that you can relate the index to very concrete mathematics. Special function which has a name was very, very important. So here is this definition of elliptic gamma function. It's extremely simple function. So if you can think of the numerator as coming from counting fermionic modes and a denominator as counting bosonic modes. And importantly, for what we will say later on, it is an infinite product. It's not trivial, but rather simple function. So you compute this index in the UV, you have a free theory in the UV. This is some non-trivial index that you obtain. But then you can entertain a very, very simple deformation. Just give a mass to these fields. Just turn on a deformation, which is Q tilde. Then in the infrared, you gap the system. You don't have anything. Basically, you only have a vacuum. So what you expect is that you only, like the index will be equal to 1, because you don't have any modes, any interesting dynamics in the infrared. And the way you do it in the index, as we discussed in general, you specialize some parameters. So when you turn on this mass deformation, you break U1R symmetry. So you set this combination of fugacities PQ over T to be equal to 1. And then this index, you simply literally plug PQ over T equal to 1 like in these expressions, and you get this expression for the index. And magically, this infinite product cancels out between these two elliptic gamma function, and you get exactly something which is equal to 1. So this is how the index is invariant under renormalization group flows. Of course, here we said that the index of the infrared fixed point also tells you something about the UV. Here it is some trivial information. You can infer from this that, okay, the theory in UV has some vacuum, but not anything interesting. But you get information which is consistent with renormalization group flow. Another thing which will be important for us later on is that you can discuss not only mass deformation or more generally superpotential deformations, you can also turn on vacuum expectation values. And there things are slightly more complicated, but the idea is exactly the same. Say you have an operator O, which parameterizes a moduli space, and you want to turn on a vacuum expectation value for that operator, and say that operator contributes to the index in the UV with some value, with some weight B, then necessarily there is a 1 over 1 minus B term in the index. There is a pole in the index because you can take any power of this operator. Like there is no chiral ring relation for that operator for it to parameterize direction in a moduli space. And then a prescription to compute the index in the infrared is not just set B equal to 1. Setting B equal to 1 will lead to a divergence of the index. So what you do, you compute the residue of the index. Okay, so to compute the index of a theory after you do a vacuum expectation value deformation, you compute, you have a pole divergence in the index, and you compute the residue of the index. Okay, so these are very well known statements about supersymmetric index that we will soon use. So B is anything. B is a combination of all the fugacities. Like if this operator has an R charge, global symmetry, so it's combination of fugacities which parameterize all these symmetries. And you need to set that combination to 1. So if you wish, if you think you break some combination of R symmetry and global symmetry when you turn on this web, and this is encoded in this parameter B. Okay? And thank you for the question. Please ask me at any point. Okay, so this is a general n equal 2 index, and the general story of how the index is invariant under a normalization group flows. So now let us discuss a very special beast, which is called the Schur index. And we will say something a little bit surprising about interplay of this Schur index with renormalization group flows and very soon. So Schur index is just a special version of the full index. It's not some new beast that you compute. We had this general index depending on parameters P, Q, and T. And to compute the Schur index, you just set T equals to Q. That's all you do. It's this setting T equals to Q is unrelated to renormalization group flows. You just compute not the most generic quantity that you can compute, but it so happens that if you do this specialization, this index has a lot of magical properties. So first of all, when you set T equals to Q, you do nothing to P. But when you look at the definition of the index, the index is consistent, like all the fugacities that you see here. They are commuting with not a single supercharge that you started with, this Q1 that we had before, but there is another supercharge with which the charges that appear that couple to the fugacities in the index commute. So this, because of that, the dependence of P disappears from the index. Again, because this number which appears here is some combination of anti-commutator of supercharges. So you didn't do anything to P, but it just disappears. It will cancel out in the definition of the index in the same way as beta canceled in the definition of in the original definition of the index. Now, importantly, this Schur index, to define it, in the end, you need only the SU2R symmetry and the J1 and J2, which are the isometries of S3. You don't need the U1R symmetry. So naively, at least, it seems that you can compute the Schur index for non-conformal theories. Now, this was shown rigorously in a talk by Thomas Dumitrescu almost 10 years ago, but there is no paper. So if you know Thomas, you should push Thomas to actually publish that result. So it is a little bit of a naive argument that this index doesn't depend on U1R, and thus it should be computable for non-conformal theory. And what these people did, they defined the Schur index as a partition function and showed exactly what background fields you need to turn on, even for non-conformal theory, for this index to be well-defined. Another thing that I want to stress about the Schur index is it is naively a Higgs branch object. Okay, why it is a Higgs branch object? Well, first of all, Higgs branch operators contribute to the Schur index. And second of all, naively, the Coulomb branch operators do not contribute to the Schur index. We said that the dependence on P in the Schur index disappears. If you look on Coulomb branch operators like trace phi to the n, where phi is a joint field in the n equal to vector superfield, and you set q equals to t, so q cancels in the contribution of this operator to the index, it only depends on p. But since p cancels out in the index, somehow this operator, these Coulomb branch operators, have to cancel against something else. So naively, these are very Higgs branchy. The Schur index is a very Higgs branchy object, but nevertheless, Schur index was found to be indirectly related to Coulomb branch. And one such relation is due to Cordova and Chow originally. And interestingly, you can compute the Schur index by going on the Coulomb branch and computing something which is called Kontsevich-Soibelman wall-crossing invariant. And it is exactly given by the Schur index that you compute at the CFT point. Okay, So, and there are some understandings of this recently, but I will not go into this. Of course, maybe the main claim to fame till now of the Schur index is its relation to VOA, n equal to VOA correspondence. So these authors have discovered that every n equal to theory has an underlying two-dimensional vertex operator algebra associated to it, and the Schur index is just the vacuum character corresponding to that VOA. And recently, there were many more interesting observations. For example, this relation of Schur to SYK, which is a little bit mysterious. And I guess Jörg will talk more about, you will not talk about. So Jörg will not talk about his paper. But it is interesting. Not that I know. There is this very recent paper. It's as far as I understand, it's just an observation. Okay, it's not. But what I want to stress about the Schur index that it leads to a lot of such observations. That there have to be. Sometimes we understand these observations, sometimes we don't. And I will present another observation that I don't understand, but I find interesting. So I said that I will present an old puzzle, and this old puzzle, it has something to do with this Schur index. So this is a very simple-minded puzzle. So as we said, the index is, you don't need U1R to define it, you only need SU2R and this SU2J1, SU2J2. So in particular, the Schur index seems to be consistent with the mass term. So you can turn MQQ tilde, and the Schur index is consistent with this deformation. Again, this is a little bit naive statement because you need to define the Schur index precisely as a partition function, but I will soon make this statement more precise in terms of something you actually do to the index. Okay. However, if you compute the Schur index, you just set in the full index of Q and Q tilde Q equals to T, to obtain that the Schur index is given by a theta function, 1 over this theta function. And this thing is not equal to 1. Okay, this is some non-trivial function. So how come the index is consistent with turning on a mass term? And we said the index is an RG invariant, and if we turn on a mass term, then the index has to trivialize, but this thing is not equal to 1. Okay? On the other hand, we already discussed that if we take the full index, depending on P, Q, and T, and set the fugacity so that we break U1R symmetry, so we set PQ over T going to 1, the full index does go to 1. So what the hell is going on here? And of course, the answer is extremely simple, and there is some order of limits involved in this computation that we need to understand. Okay? So the order of limits is extremely simple. So to take the mass deformation, we set QP over T equals to 1. So this is consistent both with giving a mass to QQ tilde, and actually, if we are in a gauge theory, this is also consistent with giving a vacuum expectation value for Coulomb branch operator. So I mentioned that the weight of the Coulomb branch operator in the index is QP over T to the power n. Okay? So if we set this equal to 1, this is consistent with going on the Coulomb branch or just giving masses to all the operators. On the other hand, the Schur limit is Q equals to T. So look at this, if we set Q equals to T, then and QP over T equals to 1, so we do mass deformation and the Schur index, it is as if we also set P equals to 1. But I've mentioned that the index of the full index of the chiral field is given in terms of this infinite product. And if we set P equals to 1 in this infinite product, we just get ill-defined expression. We get something to the power infinity. So it's very, very ill-defined limit. So this is the reason why we have something weird happening. So we have an order of limit issue. If we take first Schur, we set Q equals to T. The index is independent of P. In particular, it is consistent with P equals to 1. And this is like a technical sense in which it is consistent with turning on a mass term. So it is consistent with setting on QP over T equals to 1. But since the index is independent of P, nothing is singular when you first set Q equals to T and then P equals to 1. But if you reverse the order of these limits, you first set P equals to 1, then the index badly diverges. If you wish, if you set first QP over T equals to 1, the index trivializes, it's equal to 1, and it's also consistent with Q equals T and not depending on P. So since we have this orders of limits issue, we can try to exploit this fact. And can try to regularize the limit that we are taking. So what we will do, we will take both the mass limit and the Schur limit. We will set P equals to 1 minus epsilon, and eventually we will send epsilon to 0. So we'll take P equals to 1, and then we will parameterize T in such a way. So if we set epsilon equal to 0, again, QP over T is equal to 1, and we are in the massive and Schur limit. But we will turn on this parameter alpha. And the limit actually, when you study how the limit behaves, it will depend on this parameter alpha. In particular, the index of a hypermultiplet in this limit is given by this simple expression. So it's just given by the Schur index of a hypermultiplet, but to the power alpha. So when alpha is equal to 1, we get the Schur index. When alpha is equal to 0, we get the massive index, but we can interpolate between the two with this parameter alpha, which can be at the level of hypermultiplet. It can be any number, any real number, anything that we want. So again, I stress that alpha equals 1 is Schur, alpha equals 0 is mass, but alpha can be anything we want. So we can then define something we will call generalized Schur partition function when we take a general index, which depends on P, Q, and T, and we parameterize P, Q, and T in such a way and set epsilon equals to 1. I will refine this definition slightly on the next slide. Okay, so in general, when we will do that, the index will have an expansion in Q with integer powers in Q, but with coefficients which will be functions of alpha, and it will, for general values of alpha, the coefficients will not be integer. So that's why I call it a generalized Schur partition function. Now, I want to stress that this taking some kind of this limit is not new. This was done by Cecotti, Song, Waffa, and Yan 10 years ago, but with a different motivation. The motivation that they had is to connect, to study more this relation between Kontsevich and Soibelman wall-crossing invariant and the Schur index. And in that invariant, there is a monodromy matrix. And what they wanted, like the trace of that monodromy matrix corresponds to the Schur index, and they wanted to relate powers of that matrix, traces of powers of that matrix to these types of limits. And in particular, they looked on negative integer values of this alpha and had a slightly different definition of the index. Yes? Oh, it's just, I don't have to do that, but then this log Q will appear here. It's just a parameterization that will give some nice result in the end. It's notational thing. So let's discuss it later on. The short answer is that I don't have, but the long answer is that we can discuss. Like there is some natural. The short answer is that I don't have. There are several answers that I have, but let us discuss it later. Alpha can be anything. So we will get to integer coefficients soon. So I just take the index and I take a limit. I don't care whether I can get the integer coefficient. I start from the index with integer coefficients. I just take a limit. Whatever I get, that's what I get. So the integer coefficients will be important momentarily. That's a good question. I don't know how to do. Then your questions are related. We will see it. But I don't know how to do more than one parameter. So naively, it's the same supersymmetry as the Schur index because it's basically the same thing but regularized different. So I don't know what I don't know exactly how to answer this question. So if you wish, since you regularize some very divergent expression, the regulator, like you start from the index which only preserves one supercharge, you regularize in some way, and then you take this limit. For certain value of regulator, you preserve more supersymmetry, but I don't, kind of the most robust answer is that it's the same supersymmetry that the original index preserves. But I don't have an answer. It's a very good question. Yes, how it will be related to chiral algebra. But again, some of what you ask will come up in 2 slides. Yes, so these are excellent questions. I don't have an answer, but we'll get to some of the answers soon. Okay, so next what I want to do is just refine the definition a little bit. And the reason that I need to refine the definition is that PQ over T goes to 1 is also consistent with giving a VEV to the Coulomb range operator. And as we have discussed, if we give a VEV to some operator, to any operator, the index actually has a pole divergence. The order of the pole is the number of operators we gave a VEV to. So when we just set this epsilon to equal to 0 in the index on the previous slide, this expression will actually diverge, but it will diverge in a simple way. It will have a pole-like divergence because of the Coulomb range operators. So really, to define this partition function, we just strip the singularity, this pole singularity, in the definition of the index. So here is an example of an index of a gauge theory. So it's extremely simple. So you get this expression, and the only thing different from the Schur index is that you have the integrand that you have when you compute the index is alpha, which is not equal to 1. When you are in the Schur case, you simply set alpha equals to 1. When you compute this more general partition function, you take all of the integrand to the power alpha. Importantly, often people split the Haar measure from the rest inside the integral. You take also the Haar measure to the power alpha. When you compute the limit of the vector multiplet, not just of the hypermultiplet, that's what comes out of the limit. Okay? And you can compute this thing. Again, alpha equals 1 is Schur, alpha equals 0 is mass. And in principle, any alpha makes sense, but if you take negative alphas, then you will have divergences on the contour of integration. You need to treat that somehow. I don't want to deal with that, so I will assume that alpha is a positive real number. Okay? But probably this can be dealt with also. Okay, so this is the definition of this Schur partition function. Yes. So the way I will think about it, this is a good question, of course. I will expand. I will take some value of alpha if it's fractional is okay. I will just take the integrand and expand it in Q, and then we'll compute it. So that's how I think about it. Yes, and you can ask what analytical structure of this function is. Okay, so this is just a definition of some quantity. But remember that the quantity we constructed is consistent naively with mass deformations, although it is obtained at some regularization. So we can ask whether something interesting is encoded in this function. In particular, we will ask the following question. So if there are two CFTs, CFT1 and CFT2, which reside on the same Coulomb range, so you can obtain one of these CFTs as a Coulomb range deformation and mass deformation of the other CFT, are there these Schur partition functions, are the Schur partition functions of the two theories related in any way? Okay? As we had in the beginning, if we have an RG flow between theories which are related by some relevant deformations, the indices are related. And the question is here, are these functions non-trivial? We saw that they are non-trivial, but do they tell us something about all the theories which are connected by renormalization group flow? And here what we do an experiment. We ask this question. I don't know how to answer this question in general. So I perform a mathematical physics experiment. I just compute this function for some theory. So the simplest theory I can think about, which is interacting and has a Lagrangian, is an SU2 conformal SQCD. So SU2 and F equals 4 and equal to theory. This is the Schur partition function when I take this alpha parameter equal to 1. So this is also the Schur index of the theory. Okay. But then I look on the theory with general values of alpha, and then the coefficients in this Q expansion will be complicated numbers for general values of alpha. And then I ask this question, a question of the sort that you asked, for which values of alpha I do get integer coefficients in the expansion. Okay, so here I added this hat to the index, and this hat means that I actually normalize the partition function. If you compute the partition function that we have defined, it will not start with 1. It will start with some number, and then it will have Q expansion. So we just divide by the Q to the 0 coefficient to define this partition function with a hat. And we ask, when do we get integer coefficients? And then we look on fractional values of alpha, and we see that for 1/5, 1/3, 1/2, we get integer expansions in the index. And this one can show that if we interpret this partition function as a Schur index of some theory, the coefficient of Q has to be the dimension of the global symmetry of the theory, based on very, very general arguments. And then you see that here you don't have any symmetry. Here it seems that you have an SU2. Here it seems that you have an SU3. And when you look on the whole of this expansion, you see that the expansion matches Schur indices of very well-known Argyres-Douglas theories. So this is called A0, A1, A2, and this name is according to the global symmetry of these groups, of this theory. So you see that partition function of this SQCD with alpha equals 1/5 is equal to Schur index of another theory when you set alpha equals to 1 for that theory, and so on. So there is some relation between these theories, and that as soon I will mention, these theories are residing on the same Coulomb range. You can do other things. You can find other alphas, say alpha equals 2, 3, and 5, which also give integer coefficients, and the expressions that you get match Schur indices of E6, E7, and E8 Minahan-Nemeshansky theories. These Argyres-Douglas theories are, in a sense, down the flow from this SQCD. These theories are up the flow from this SQCD. So again, it seems that there is some non-trivial relation between different theories, between these partition functions of different theories residing on the same Coulomb range. Okay. Yes. So let's discuss it in the end. So this is also related to what this parameter alpha is. Let's discuss it in the end. Okay. Okay. So this is the full statement. So this is the full table when like all the values of alpha for which we get integer coefficients in the normalized index. So we get this E8, E7, E6. So we are computing the index of this SU2 theory, which has a D4 symmetry, and we have Argyres-Douglas theories, and there are also these values of alpha for which you get integer coefficients, which do not naively correspond to vanilla quantum field theories. They do correspond, like the expressions you get are characters of certain vertex operator algebras, which have these weird names. Some of them are conjecturally quantum field theories that one can build. Some other are related to some other physical constructions. But importantly, you get all the physical theories that you can connect by renormalization group flows here. And again, statement is very simple. If you take any of these physical theories, say E8, E7, E6, and so on, and you compute the Schur partition functions for them, it is related to other Schur partition functions, but there is a non-trivial map of these alpha parameters. And this often happens even when you compute indices, like you do superpotential deformations, or you study, say, two theories which conjecturally flow to the same fixed point. You need to match in some non-trivial way the global symmetries of these two theories in order for partition functions to agree. And here there is a non-trivial match of these alpha parameters. So this I don't know what would be the 4D theory which will give this Schur index. So there is the one claim that actually was communicated to us by J1 after we put out this paper, that they have a suggestion for a to the half. They have some n equal 1 Lagrangian, which flows, they claim flows to an n equal 2 theories, which has the same Coulomb range dimension, no Coulomb range operator, with the same Coulomb range dimension and same anomalies. So it's a little bit special construction, but there is a claim that maybe it corresponds to some physical theory. But all the others, I am not aware of physical. So all of these have 2D meanings. All of them have a 2D meaning. The question is about the 4D meaning. Maybe, yeah. So in this case, there are various heuristic arguments, but in general, I will show soon another table where we don't find this happening. So it's very experimental, so I don't know the answer to this question. Here, indeed, you are right. There is some symmetry, but in general, I don't think it's the case. So these are some two-dimensional theories with negative central charge, and they give they were classified, and this is what is called this Deligne-Svitanowicz series, CFTs, and they have this, like the expressions that we get, setting say alpha equals to 4 and so on. I don't know. Okay, those things I don't know. The things which we know are physical field theories. They are related by flows. So you can wonder about this if it is indeed a physical theory, what that means. But that's a conjecturally physical theory. Okay, so let me make a comment. So you see, we started from a theory which has an SO8 symmetry. That's what this is the 28 that we see here. Here the symmetry is smaller. We go down the flow, so it might be not very surprising. But here we get expressions for the partition function, which with 78, which is the dimension of E6, dimension of E7, dimension of E8. But this theory clearly doesn't have E6, E7 in E8. But in some limit of parameters, you get expressions that seem to know that up the flow, there are theories with these big symmetries. I don't know the physical meaning of this statement. So you can actually unpack the computation of taking these alphas equal to 2, 3, 5, and so on. And you see that, for example, for this D4 theory, you understand, of course, where the 28 comes from. These are the moment maps. But these weird numbers that appear here, which lead to 78, some of them come from Q squared. Some of them come from Gauginos, like when you actually perform the computation. So for me, it's a little bit of a magic how you obtain this 78 and 133 and 248. I don't understand why you get them. I just observe that you get them. So it's an interesting question, like why do you get these numbers exactly? So how this D4 theory knows, in a sense, that it comes from something with a bigger symmetry. So again, there is some heuristics that you can understand. Now you have this experimental result. You can try to understand it. So it seems if you a theory and take alpha bigger than 1, you obtain theories up in the RG flow. And if you take alpha smaller than 1, you get theories down the RG flow. And I remind you, alpha equals to 1, you obtain the Schur index of the theory you started with. There are various things that if you believe this understanding that IQ alpha captures theory, the renormalization group flow, for example, captures the E8 theory in some way, we don't have at the moment a constructive algorithm how to compute this Schur partition function for the E8 Minahane-Meshansky theory. So this gives you actually a prediction for the Schur partition function for the theory. For Argyres-Douglas theories, we have Lagrangians constructed by Maruyoshi and Song, and we can compare the Schur partition function that we get depending on parameter alpha to what would they get, and these things agree. So it gives you some prediction about things that we don't know. there is some relation to modular differential equations and to VOAs. This is, again, this is something we don't understand, but it seems that for general value of alpha, the Schur partition function solves the LMD, some modular differential equation. What is the meaning of that? I don't know, but this is something interesting. So after all of these success stories that I discussed, I want to stress that this doesn't always work. So for this orbit of renormalization group flows in which this SU2 SQCD lives, it seems that Schur partition functions of all theories are related, but you can look on other orbits. For example, you can look on n equals 4 SU2 theory, and there are n equal 2 theories with this data. Delta is the dimension of the Coulomb branch operator, which flow to this n equals 4 SU2 theory. But the Schur partition functions, as far as we could check, they are, of all of these theories, are unrelated. We could not make this simple match of these theories of Schur partition functions of the theories in this sequence. So then the question is, okay, sometimes something works and sometimes something doesn't work. The question is what works, when it works, and why it works. So one thing that you can do, you can ask this question and do more experiments, compute more partition functions of more theories which are related by RG flows, and see when the partition functions are related. So again, an experimental rule that we came up with is that if the central charges of two theories are related in a simple way, in a correlated way with the dependence on, with the relation of the dimensions of the Coulomb branch operators, then the Schur partition functions are related through this alpha, as we have discussed before. And there are infinite sequences of examples. So for example, instead of starting with SU2 with 4 flavors, you can start with SUN and 2NF flavors. And then play with alpha, and you obtain indices of Argyres-Douglas theories, or of a theory, this R2 to N minus 1 theory, which is a generalization of the E6 theory. And here, to the question of Matthias, there is a 1 over n here, but there is no n. Like if you plug it an n, you don't get integer coefficient. For 2 you get, for general you don't get. So in general, this is not a rule that, that we could come up with. And with USP, there is another generalization with starting with USP to n. Again, it's another generalization of SU2, and you obtain indices of other Argyres-Douglas theories. So I just want to stress when you set this alpha parameter to be not integer, this is related to Pavel's question, it's hard to compute these partition functions. You need to compute this numerically, in a sense, and this is a hard computation. So the checks that we made here are not extremely impressive, but there are checks, rather non-trivial checks that we made of these expressions. No, we never get an n equals 4 theory. Say it again? I don't know. We try to play this game, like why things work when they work and why they don't. So we had a lot of conjectures. I don't know. So that might be one such conjecture. Another is something called extended, whether you have extended Coulomb branch or you don't have extended Coulomb branch. But I don't know. There is this experimental observation, but I don't know what the physical means. These are high rank. All of these are high rank. Okay, so these are dimensions of the Coulomb branch operators. So they have several Coulomb branch operators. Okay. Sorry? These are all unequal to. Not on the low side, but there are things like there. You can have free theories, of course, but there are theories which flow to them. Okay. So my guess is that there is a generalization of this procedure, like this simple map. Map doesn't work maybe for most general theories. It works only for theories which satisfy the condition here. But the theories which don't satisfy this condition, there is some other map that we just didn't find of the Schur partition function. Okay, how I'm doing with time? I'm out of time.
There's a 5 minutes question session.
Okay, so yeah, experimentally, yes, but of course we did not go over all the theories. We went over many examples and it seems to work, but it's an experimental result. So let me just finish very quickly in 1 minute or 2 minutes, and that's it. So once you understand that you can, at least in some cases, obtain these Schur partition functions of some strongly coupled theories like E6, E7, E8, or Giras-Douglas theories from Lagrangian theories by playing these tricks with alpha, you can concatenate these constructions. You can, for example, obtain a theory, in this case, the index of some Giras-Douglas theory by playing this trick starting with this SU2 SQCD, then add to it some free matter, gauge some global symmetry, and obtain indices of new theories. So you can play this game with, like, you don't need to get to take the same value of alpha when you construct complicated theories. Once you understand this trick, you can play certain games with it. This is one comment that I want to make before finishing. Another claim I want to make, which is rather trivial, is that this partition function has to be consistent with S dualities, something that didn't play a role in what I was discussing till now. So for example, this SU2 SQCD in this class S construction, when you construct it as a compactification on a sphere of 2,0 theory, it corresponds to compactification on a sphere with 4 punctures. And there are different duality frames when you play with how you do pair of pens decompositions of this sphere. And in this Schur partition function, this corresponds to switching various parameters. The integrand of the integral doesn't satisfy the symmetry of exchanging the punctures, but the integral does. And it's a very funny expression because it works for any value of alpha. So like the integrand is not invariant under this symmetry, but the integral is for any value of alpha. And this was mathematically proven for the SU2 case by De Boot long ago, and only this year for the SUN generalization of this statement. So let me summarize. So we have discussed a definition of a generalized Schur partition function. It is defined by taking a regularized mass Schur limit of the index, and naively it is consistent with mass and Coulomb range deformations, and at least in some cases, we have seen that this partition function can be related for theories related by this renormalization group flows, but always. So this is a non-trivial partition function which you can compute, and it seems to be the same, at least in some cases, when theories are related. I don't understand why and when does this work. Okay, and then I can answer some of your questions, but let me stop here.
One quick question.
So that might be related to this fact that all of these partition functions, they say they basically solve the same LMD where this alpha is a parameter. Okay, so maybe that's another criterion when it works. Then you have like theories which are connected by these flows. It's the same differential equation with alpha being a parameter in that equation. So that's definitely true in this case. So McDonald index, I don't think it will work for McDonald index because it's in McDonald index. So what is special about Schur index is that you don't set by brute force some parameter to 0. So McDonald index is setting p equals to 0. For example, in this particular case, all the magic came from the fact that p equals to 1 was a singular limit. It's true that the Schur index is independent of p. In particular, it's consistent with p equals to 0. But the interesting part came from the fact that it is actually consistent with p equals to 1. McDonald is p equals to 0. So it's also consistent, like it's a specialization of McDonald's gives you Schur index, but I don't see how it will be directly related. Okay, so in particular, I don't think it will be consistent with the mass limit, the McDonald limit. Yeah, this is a good point. You mean the defect? You mean like line defect or?
Whatever, line defect.
I don't know. This is a good question because we are basically regularizing the Schur index, and the Schur index admits, like the supersymmetry of Schur index admits, you can compute Schur index in presence of line defects. So I think it's a good question, but I don't have an answer. Just to answer Kole about the 3D limit. So, and it's also a question, what is parameter alpha is? So since we're sending the P goes to 1, so that actually looks like a 3D limit. Because if we send P and Q and T, all of these fugacities to 1, this is a 3D limit. So it's, in a sense, I think it's some kind of mixed 3D, Schur or whatever limit. And in that sense, this alpha is like a real mass parameter for some combination of R symmetries. So in this respect, and this is also like an answer to your question. This is a very naive one way to understand this alpha. Another is like you are shooting in some direction on the Coulomb range, like with this alpha. So sometimes you hit theories, sometimes you don't hit theories, but it's very, very vague state.
Okay, if there are no other questions, let's thank the speaker again.